So we will continue chapter 7 review, right? We started yesterday, and we'll continue with problem number 5. And so here we are completely switching gears because chapter 7, first part was on gases mostly, but now we will look at intermolecular attractive forces. So when you have a list of molecules like that and you are asked to list all intermolecular attractive forces that are in play between molecules of each substance. So you have to imagine that you have these substances and it's pure substances just by themselves. So what will be the forces of attraction between the molecules of those pure substances, right? We are not thinking about between molecules. It's just the pure substance, molecules of that substance only. So the intermolecular attractive forces, there are 3 or 4 kinds, but when you have this kind of question, you only want to focus on the 3 that are London dispersion forces, dipole-dipole interactions, and hydrogen bonding. The 4th one is ion dipole interactions, but they only can occur between ions and polar molecules. And so that means you have 2 different substances mixed together. So here it's out of the question here, you would not be using that one, right? So, so let's start with Br2. So Br2, it's a molecule made of 2 bromine atoms. It's one of those diatomic molecules that you find in nature. In this is an element, but it's a diatomic molecule. Element because it's made of only one type of atom. So it's a good idea to visualize the Lewis structure, or at least see what it means. You know, it's just 2 bromine bonded together. Why you want to visualize the Lewis structure? It's because you will have to determine if it's polar or not, because that determines the type of intermolecular attractive forces that you will see between the molecules of Br2. So can you tell me, is Br2 polar or not? You can answer in the chat and tell me polar or non-polar for Br2. Yeah. So Br2 is non-polar, yes. It is important to know that because then what would be the attractive forces that will be playing between the Br2 molecules? So there is one that you should always list for all molecules, yes, and that's the London dispersion forces. Why? Because all molecules experience that. It's when so this occurs when so within molecules you have an electron cloud, right? Around the nucleus you have the electron clouds of the atoms, and electrons are roaming around in that space, you know, symbolized by the electron cloud, and they keep moving. It's a bit like gaseous particles. They keep moving in there, and of course they are tend to be within specific areas, you know, orbitals and shells and all of that, but still they keep moving. And for example, at an instant you can have a lot of electrons on one side of the electron cloud, much more than on the other side. And so on the side where the electrons will gather, you will have a partial negative charge, and on the side where you're missing electrons, you will have a partial positive charge. And those partial negative charges will be attracted to partial positive charges in another molecule, right? And so that's what London dispersion forces are about. It's about temporary, you know, partial dipoles that you observe because the electrons move around. And because they keep moving around, it only is true for an instant, and then in the next instant they will move to another area, or be well spread, so you may not have a partial negative charge and partial positive charge. So London dispersion forces are really instantaneous forces, so they keep changing. But because all molecules have an electron cloud, they all experiment that London dispersion forces. So now, can Br2 experience dipole-dipole interactions? You tell me yes or no. So dipole-dipole interactions. So for molecules to experience dipole-dipole interactions, they need to have dipoles, right? Do we have a dipole here in Br2? No, right? So dipole-dipoles cannot be happening here between molecules of Br2, because Br2 are non-polar molecules, and a dipole, right? A dipole, I will just write it here. Dipole means you have a polar molecule, right? And then the dipoles of one molecule is attracted to the dipole of another molecule. And in the case of Br2, because it's non-polar, there is no dipoles. So it cannot experience dipole interactions. Can it experience hydrogen bonding? So tell me yes or no. So can Br2 experience hydrogen bonding? No. No, because there is no hydrogen, right? Br2 is just made of bromine. So there is no way you can have hydrogen bonding. So it really only experiences London dispersion forces. Okay, so let's move on to HBr. So it's a good idea to decide right from the start if it's a polar molecule or not. So look at the electronegativity difference between H and Br. And so the electronegativity difference, Br is, let me insert that delta electronegativity. It's going to be 2.8 minus 2.1, and that's 0.7. So we have an electronegativity difference between H and Br that is 0.7. So HBr is it considered polar or not polar? Are you sure? So if you look at so let me change my share here. If you look at this reference, yes, no worries. So go to page, hopefully you have this, in your hands, but you need to have this page of electronegativities and the page of electronegativity difference, and also the shapes of molecules will be helpful here. So anything that you used for chapter 4. So here you see that an electronegativity difference of 0.7 is between 0.5 and 1.9, which means it's considered polar covalent, right? So the HBr bond is polar covalent. So it's polar. It's polar, and there is only those two atoms, so it's a polar bond and it's a polar molecule, right? Because it's just that bond. So it's polar. So let's list the intermolecular attractive forces. And here, like we said, you should always list London dispersion forces. because all molecules have an electron clouds and will experience that. So we have London dispersion forces. Now the question is, do we have a dipole-dipole interactions? So let me write it: dipole dash dipole interactions. Do we have that? So yes or no? Yes, because we have dipoles, right? As long as we have a polar bond that is not cancelled here, this is called also a dipole, right? Dipole, imagine an arrow. The arrow would go from H to BR, you know, pointing towards BR. And so this is considered a dipole. And so one dipole would be attracted to another dipole. So the pointed side would be attracted to the plus side of the arrow of another molecule. And the positive side of the arrow would be attracted to the negative side of another molecule. So that's why it's called dipole-dipole interaction. So yes, they do experience that. Now, the question is, does HBr experiences hydrogen bonding? So hydrogen bonding. Question? No, because so for hydrogen bonding, you need H to be bonded to N, O, or F. Nitrogen, oxygen, or fluorine, the most electronegative elements. And we don't have hydrogen bonded to any of these. Instead it's bonded to bromine. So you cannot have hydrogen bonding. So no hydrogen bonding. You stop there, right? So that's for HBr. Let's do H2O. And let's just remind, let's copy that first. So is H2O a polar molecule? And hopefully you know this by heart now, because you should have seen water come up a lot. But let's calculate the electronegativity difference between O and H. O is 3.5, H is 2.1, and the difference is 1.4, right? .4. So the OH bond is polar. So we have two polar bonds. You remember the shape of the molecule of water? It's bent, right? Hopefully I don't have to show it here, but it's bent because the oxygen has two lone pairs on it, plus two single bonds. That means, so let's go back to that here. So around oxygen of water, we have 4 electron groups, 2 bonding groups, 2 lone pairs, right? So it would be, you would be looking at the last line. Actually, water is there, you know, last line here, and the example is water. So 2 bonding groups, 2 lone pairs around oxygen, and so it's a tetrahedral electron geometry. And then it's a bent molecular geometry. So water is bent, and you have the model showing how it's bent. And so those two polar bonds, the HO bonds pointing towards oxygen, they add up into one net dipole that goes between the two hydrogens up towards the oxygen. You know, if you look at that model here, it goes straight up from between the hydrogens up towards the oxygen. So this is a polar molecule. So the bonds are polar and H2O is polar. Okay, so let's decide now what are the, sorry, up. What are the intermolecular attractive forces? So as always list the London dispersion forces because they are always there for all molecules. Then the question is, do we have dipole-dipole interactions or not? So tell me yes or no. Yes. Yes, we do have dipole-dipole interactions because the molecule is polar. We have that net dipole, and so that will attract other net dipoles, and they will arrange themselves so that the arrows are all, oriented in one direction. And now the question is, do we have hydrogen bonding between molecules of water? So tell me yes or no. Yes, water is experiencing hydrogen bonding because H is bonded to O, and so the hydrogens will be attracted by the oxygens of the other molecules, and then the oxygens will be attracted to hydrogens of other water molecules, right? So we have hydrogen bonding. So water is really very strongly held together by all these forces. Okay, let's do C4H10, which is butane here. Butane. So, so hopefully by now you know that the electronegativity, but let's do it just to consolidate that. Electronegativity of C is 2.5 minus electronegativity of hydrogen is 2.1. That's a difference of 0.4. And according to the electronegativity table here, a difference of 0.4 is considered non-polar, right? So electrons are equally shared between the carbon and hydrogen. So it's a non-polar. So the CH bond is non-polar. And otherwise you have carbon-carbon bonds in there, and they are also non-polar, right? Because when it's two of the same atom, it's necessarily non-polar. So butane is non-polar, right? When you have no polar bonds, there is no way your molecule can be polar. So then butane is non-polar because it has only non-polar bonds. So, and hopefully I didn't show that, but maybe, it's CH3 bonded to CH2, how many times? Yeah, so 2 times. CH2 and then CH3. You really want to see it like this. It's a chain of carbons, and each carbon has hydrogens bonded to it to complete its octet. So it's just a chain of carbons bond, with hydrogens around them. So it's non-polar. So now let's list intermolecular attractive forces. Let's put down London dispersion forces because all molecules experience that. Now let's decide, do we have dipole-dipole interactions? Yes or no? Tell me. No. And do we have London dispersion? No, not London. Hydrogen bonding, I mean. Do we have hydrogen bonding? Because we have hydrogen there. No. Yes, very good. Hydrogen is bonded to C, so there is no possibility for hydrogen bonding. Okay, so no hydrogen bonding there, so just London dispersion forces only. And that's very typical of non-polar molecules, right? When you decide your molecule is non-polar, most likely it will only experience the London dispersion forces because there is no dipoles then. And then, typically when hydrogen is bonded to oxygen, nitrogen, or fluorine, you have polar bonds. So then there's no way you can have hydrogen bonding either. Okay, so now let's rank these 4 substances in order of intermolecular strengths from the weakest to the strongest. So let's do this here. So which one would be the weakest? The molecule that experiences the weakest intermolecular attractive forces. So is it Br2, HBr, H2O, or C4H10? So you think it's Br2? Yes. So you have to decide, is it Br2 or is it C4H10, right? Because those two only experience London dispersion forces. And you're right to think it's Br2 because and the reason it's because it's a smaller molecule than C4H10, right? If you look at these two, C4H10 is a larger molecule, so its electron cloud will be larger. And when you have two molecules that only experience London dispersion forces, the London dispersion forces will be stronger for the larger molecule because the electron cloud is larger. So when you have an imbalance of electron distribution or electron density, it will create a slightly larger delta minus and delta plus, partial positive charges and partial negative charges. And so that will make the London dispersion forces slightly stronger. So between these two, between these two, Br2 will be the one that experiences the weakest intermolecular attractive forces. So let's put them together like that. And then what comes after that? Tell me, what is having the moderate intermolecular attractive forces between water and HBr? Yes, HBr comes after that because water is the strongest. It has all 3 kinds of forces, hydrogen bonding, dipole-dipole interactions, and London dispersion forces, while HBr experiences only London dispersion forces and dipole-dipole. So that's the way it will be, okay? So that would be the answer to that question. So from weakest to strongest, let's just make it the weakest here. Strongest, just to be sure we understand. Okay, so which substance would have the highest boiling point? Because those forces of attractions, they will, delay your change of phase from liquid to gas if there is a lot of forces of attractions, right? Yes. The highest boiling point would be the molecule that experiences the strongest forces. H2O will have the highest boiling point because it's held so tightly together that it requires more energy, so a higher temperature, to be able to break those intermolecular attractive forces and have molecules free from each other and flying around, right? So H2O, because it experiences the strongest. IMF is the acronym for intermolecular forces. So which substance would have the lowest boiling point then? Yes. So the one that will have the lowest boiling point will be the molecule that experiences the weakest. So Br2 will have the lowest boiling point because it experiences the weakest forces of attraction. So it's not held very strongly together, so it's easy to break those attractions and then have it break free and be, molecules by themselves in the gaseous phase. So which substance would have the highest vapor pressure at a given temperature? So remember what vapor pressure is. It's and it's funny here we have so let's say, for example, you have a liquid in a beaker, and the vapor pressure is the gas phase that is above the liquid, and we call that the vapor pressure. And all liquids have, but some will have more than others. And so the way to decide that is, if it's easy to get into the gaseous phase, then you will have a higher vapor pressure. So which substance would have the highest vapor pressure? Did you answer already, or? Br2, right? So Br2 would be the one that has the highest vapor pressure above the liquid, because it's held not so strongly together. So you will have vapor above the liquid more easily than, for example, in the case of water. And the reason would be the same, because it experiences the weakest intermolecular attractive forces. So which substance would have the lowest vapor pressure at a given temperature? So what should we have here? Yes, H2O. And the reason is because H2O has the strongest intermolecular attractive forces. It's held very strongly together, so it's harder for molecules of water to break free from the liquid and be, by themselves into the gas phase. Okay, so great. So that's why intermolecular attractive forces are important. You see how they determine or how they affect the boiling point and melting point, because what's true with boiling point, it's also true with melting point, the vapor pressure, etc. So this is more what is on the beginning of the chapter 7, but let's do this. So identify the 3 physical states. It's important that you visualize what is a solid, liquid, and gas, at the atomic level. So here you have black spheres that represent atoms or particles of a substance, and it's represented in its 3 physical states. So tell me, what is A? What is the gas? What is the phase of A? The gas, liquid, or solid? Yes. A is yeah, gas. Okay. So B, what is B? Liquid. And then C is the solid, of course, right? So yes. Let's make this visible. So how do we know from those drawings? Gas particles are free from each other, flying around. There is a lot of space between the particles. So that's the gas. In the liquid and solid phase, your particles are packed together, right? They are more tightly held together. There are more forces of attractions in play. And the difference between the solid and the liquid is that the liquid there are some attractions, but less than in the solid phase. And so molecules can still roll around and slide past one another. And so then there is no order. It's a random. And then the solid, there is a definite order in which the molecules are packed together, and they're packed in a, they are very organized. It's in showing a pattern or a lattice, right? So that's how you recognize the physical states. So yeah, okay. Physical state is gas state. Okay, I guess I should say that because otherwise it looks weird here. So when what are the names of the phase changes symbolized below, and are they exothermic or endothermic? So when the substance goes from phase A to phase B, and so B is the liquid phase, and so when you go from the gas state into the liquid or phase or state, yeah, that means the same thing here, phase. So can you tell me the name of that change, phase change, going from gas to liquid? How do we call that? Okay, you say it's exothermic, but you know, there is a name for the change from gas to liquid. How do we call that? And you're right, it's exothermic, but tell me the name. No. So deposition is when you go from a gas to a solid. Here it goes from a gas to a liquid. Yes, condensation is the term. Yes, it's condensation. When you go, you know, condensation is going from a gas to a liquid. It is exothermic. So what does it mean, exothermic? Exothermic in exo means exit. Thermic refers to thermal energy, and so you always are putting yourself into the place of the substance. And here, when the substance goes from a gas to a liquid, the thermal energy is exiting the substance, right? So it's releasing energy to the outside. It is really releasing energy to the outside. That's what it means. Okay, so then going from A to C, which means so going from gas to solid. So what is this called? So do you have the name for this phase change, going from a gas to a solid? I know it's not one you hear a lot, but that's deposition, right? Deposition is going from a gas to a liquid. Sorry, going from a gas to a solid. Directly from a gas to a solid without going through the liquid phase. It's called deposition. And sometimes deposition is used, for example, let's imagine you want to coat jewelry, or, you know, an object with gold, for example. And so you do that under vacuum, so a big vacuum bulb, if you will. So it's glass. It's closed, sealed. You make it. You suck all the air from there, so it's a vacuum, and you vaporize the gold. So you make it into its vapor phase, and then you throw it at the object, and the object is cold, and so when it gets reach the objects, the gold vapor will automatically become solid, and that's how you can deposit, for example, gold onto objects and have only a thin layer because gold is expensive, right? So that's called deposition, and for example, you're depositing gold onto a jewelry or something. So is it exothermic or endothermic? So tell me, is this exothermic or endothermic? Yes. Again, it's exothermic. The way to know this, so again, it releases energy to the outside. It's exothermic because you go from a very disorganized state to a very organized state. It stabilizes the substance a lot. And when you stabilize substance, you always lower the amount of energy of the substance, and that means energy has been released to the outside, to the surrounding. So that's how you can tell, if you, because you don't have to know this by heart. You should be able to think about it and deduct from the fact that a gas is a very disorganized, has a lot of energy in the particles to be able to move around like that. And then suddenly, poof, they are, you know, uh, only vibrating around a fixed position, very held tightly together, and so very stable now. There is much less kinetic energy into a solid, and so you've lost all that energy to the outside. Okay, so what is the phase changed going from a liquid to a gas? So going from a liquid to a gas, what is this called? Yes, this one is easier. We hear that word much more than deposition, for example. Vaporization, also evaporation. Let me write both because both are correct. Evaporation / vaporization, both are correct. In both words, you see vapor there, right? Vapor. It's when you're going from a liquid phase to a gas phase. And so is this exothermic or endothermic? Yes, it's endothermic. Endothermic, because as we said, going from a liquid to a gas, so the gas has much more energy, kinetic energy, to be able to move around like that and be free from each other. So going from a liquid phase to a gas phase, you need to bring energy to the substance. And so endo here, endo means inside. And saying that it's endothermic, think about the substance itself. So for the substance to go from a liquid to a gas, it needs to take energy inside. So endothermic means it will absorb energy from the surroundings and take that energy to go into the gas phase, because you need energy to go into the gas phase. Yes. So then what is going from B to C? So from a liquid to a solid. So going from a liquid to a solid. What is the name of this phase change? Liquid to a solid freezing. Yes, freezing is the term. Freezing is going from a liquid to a solid. So is it an endothermic or exothermic? So does it release energy to the outside or absorbs energy from the outside? Yes, it is exothermic because liquids becomes more stable in the solid state. It becomes more stable. There is more forces of attraction that holds the molecule together and you know, doesn't allow them to roll around anymore. So whenever matter becomes more stable, it's actually lower in energy. So the substance released energy to the outside because it doesn't need it anymore now in the solid state. So exothermic, it releases energy to the outside because the liquid. Okay, so from C to A. So C to A is going from a solid to A, so a gas. From a solid to a gas. So tell me, what is the name of that phase change going from a solid to a gas? Yes, another term that you may not hear a lot, but that is the opposite of deposition. It's called sublimation. Sublimation is the opposite of deposition. And sublimation, you go from a solid directly to a gas without going through the liquid phase, right? It's important to realize you go from a solid to a gas without going through the liquid phase. And so is it exothermic or endothermic? So going from a solid to a gas. Yes, you need a lot of energy for this. It absorbs energy from the surroundings. Yeah, you need a lot of energy to, you know, have the solid become a gas. Because the gas particles, they need so much energy to be able to be free from each other and fly around. So they need that energy to move, you know, kinetic energy. So the substance will have to absorb, so endo, take the thermal energy inside and absorb all that energy from the surrounding. It takes it from the surrounding. And we have another one. So going from C to B, so from solid to liquid. So what is the name of this phase going from a solid to a liquid? Yes, solid to a liquid. That's melting, yes. Melting is going from a solid to a liquid. And is it exothermic or endothermic? Endo, yes, endo, because the substance needs energy, you know, the solid needs energy to break the attractions that are holding the particles together so that the particles are slightly more free. to move. So you need to give energy to the particles to be able to move around and break free from the attractions. So then the substance will have to take energy inside, you know, endothermic, take energy inside and absorbs energy from the outside. Good. So those names, you know, condensation, deposition, evaporation, freezing, sublimation, melting, you need to know those names. And you know what they mean, you know, going from a solid to liquid is melting, etc. You need to realize that melting is the opposite process of freezing. And so if melting is endothermic, then the opposite process, which is freezing, has to be exothermic, right? When you know one of the process is endothermic, the opposite process will necessarily be exothermic. And if you look, for example, at evaporation, the opposite process is condensation. So if evaporation is endothermic, then condensation is exothermic. And same with sublimation and deposition. So deposition is exothermic. So sublimation has to be endothermic, right? The opposite process, the energy change will be opposite also, right? So so deposition, sublimation, they go together. Okay, so let's do the problem 9. Hopefully you still have time. Let me just... So problem 9, what is the specific heat of a metal if a 12.8 gram sample absorbs 49 joules while its temperature rises from 18.2 degrees Celsius to 26.6 degrees Celsius? So once we have that figured out, then we can answer the second question. But let's just look at this. So specific heat has been introduced in chapter 7. And specific heat is the amount of energy that a substance needs to raise the temperature of 1 gram of that substance and raise the temperature by 1 degree Celsius. And so, you know, energy is dealt with in chapter 6. So that's why maybe it comes like, you know, you don't know what this is, but joules are a unit of energy. It's actually the international system unit, but there's also the more well-known calorie, right? Calories are also the units of energy. Let me show you in the packet here, reference packet. If you go to the first page, and it may look slightly different in your version, but here, first page, reference information for Chem 121. Here you have the heat formula that says Q, and Q is the symbol for heat. It's M, which represents the mass, times delta T, which represents the temperature change, times SH represents the specific heat. So you will use this formula here, and we are given the heat in joules, we are given a mass for the piece of metal, and then we have a temperature change that we need to calculate. And then we are looking for SH, the specific heat. And so here you have some conversions of unit energy. And this is really chapter 6 here on the left side of that first page of the reference is typically for chapter 6. But you see we need it also for chapter 7. And here it shows you the relationship between calorie and joules. The capital J is the symbol for joules. And you have 4.184 joules in 1 calorie. And so calories, you have to be very careful with that unit because there is calories with a lowercase c and calories with capital C, which are two different units. because the 1 calorie with a capital C is equal to 1,000 calorie with a lowercase c. So be careful. Or another way to say it is that 1 capital C calorie is equal to 1 kilocalories with the small c. So that's the information you have in hands with the reference. So, and I know you may not have reached that point in chapter 7, and I understand if you have not. So we will need to use this formula that says heat equals m times, so it's going to be a dot, delta T, the temperature change, times SH. SH represents the specific heat. Let me put this here, SH. So that's the formula we will need to use whenever you hear about heat calculation or specific heat, you need to use this formula. So what is given is the mass. So you should recognize that G here is grams, and grams are units of mass. So we're given a mass of 12.8 grams. And we're given, so again, you may not know this, but 49 joules are units of heat. So heat is equal to 49 joules. And then we know that the temperature, and so I'll calculate the delta T already because I know we need that. So delta T is the temperature change, and here we know it goes from 18.2 to 26.6, and you always take the larger value, 26.6, minus the smaller value when you want to calculate the change, right? Equals let me calculate this. So 26.6 minus 18.2, 8.4. And so it's 8.4 degrees Celsius. Okay, so that's our temperature change. So imagine you have this small piece of metal and you're applying heat to it. You're warming it up. You measure the temperature before you start heating. It was 18.2 degrees. And you stop when it's 26.6 degrees, and you record that. And so the piece of metal has been warmed up from these two temperatures, between these two temperatures. So it took 8.4 degrees Celsius. And you know the amount of energy you applied, and it's 49 joules. And you know the mass of your piece of metal, and it's 12.8 grams. And we are looking for SH, specific heat, SH. So you have to use this formula and rearrange it such that SH is by itself, right? You solve for SH. So let me add an equation here. So if you have heat equals M delta T SH. So if we to get SH by itself here, I hope you see that you need to divide both sides by M delta T, right? By doing this, you will get rid of M delta T and have just SH. So if you do that on the right side of the equality sign, you need to do that on the left side so that it's still equal T, right? And so that means we have heat over m delta T equals to SH. Now on the right side, you have SH by itself. So that's the formula we will use. So now if we are ready to plug in the values, our specific heat will be in units of joules per gram zone per degree Celsius, which is fine. Oops, no. Ah, okay. Let me insert a new equation. Okay. So SH equals, I need to have the heat on top, and that's 49 joules. Yeah. M is 12.8 grams. And times delta T is 8.4 degree Celsius. Right? So in the calculator, you do 49 divided by 12.8. Oops. 49 divided by 12.8 divided by, so divided again by 8.4. Otherwise, if you open the parentheses after you divide, then you multiply them together. So be sure of doing this properly. Either it's 49 divided by 12.8 and divided again by 8.4, or it's 49 divided, open the parentheses, do 12.8 times 8.4, close the parentheses, because you have to tell your calculator you need to do this product before you divide with it. Equals, because if you don't do with the parentheses or divide with 8.4, then you will have a wrong answer. So be very careful with how you use your calculator. The calculator answer is that 0.455729, and the unit. You see how none of the units cancel. So then it's joules per gram N per degree Celsius. Right, and that's typical of specific heat unit, that they should be like that. They should be in units of calories or joules per gram and per degree. Yeah, let's, I forgot to run. I need to run this. Let's run this. Is it? Oh. No. Equals. Okay, how do we run this? We have 2 sig figs in the heat, 2 sig figs in the temperature change, and 3 in the mass. So we need to keep 2 sig figs. So we will keep the 0.45. That's 2 sig figs already. What comes after the 5 is a 5. So you round up. So the 5 becomes a 6, and then you drop everything after that. And it's joules per gram and per degree Celsius. Right? So that's the specific heat of your piece of metal here. And so let's answer the second question now. Is this metal requiring more energy than water to heat 1 gram of it and have its temperature change by 1 degree Celsius? So I have to write here the SH for water is in units of joule. So the specific heat for water is 1 calorie per gram per degree, which means 4.184. Let me put this in the, so that the units will look nice. And it's joules per gram and per degree Celsius. Okay, so that's the specific heat for water. And here we have the specific heat for the metal. And so is the metal requiring more energy than water to heat 1 gram of it and have its temperature changed by 1 degree? So now we have those two specific heat with the same units per gram and per degree in joules. So when you have a small number, does it mean you need more or less energy than water? You tell me if it's requiring more energy than water or less energy. So tell me more or less. Yes. So the metal requires less energy than water to get warmed up by 1 degree. And 1 gram of it. Oh, I should say that here. 1 gram of the metal requires less energy than 1 gram of water to get warmed up by 1 degree Celsius, because it's a smaller value that is needed, right? You need less joules, which means you need less energy. And that's very typical. The reason why I'm asking this question is because I want you to know that water is actually hard to heat. And that's because of those very strong attractive forces that hold the molecules of water together. And so it's hard to break those attractions and make it go from solid to a liquid, and then a liquid to a gas. And so metals, which are known to be good heat conductors, they will be easier. They will require much less energy than water to get warmed up. So that's what specific heat tells you. It tells you, gives you an idea of how much heat you need to warm up a piece of that substance. Okay, time is flying, and I don't know, do you so next problem is asking to draw the cooling curve for sodium from 1000 degrees Celsius to 0 degrees Celsius. Sodium has a freezing point of 98 degrees Celsius and a boiling point of 883 degrees Celsius. So a cooling curve is, and that's what I was doing at the beginning here. Let me copy that sentence because I cannot do it on Word. So let's copy this and share the PDF here. So let me have this text copied here. Hopefully I can paste. Yes, I don't need this. Oops. We are missing a piece, right? Yes. Okay. So draw the cooling curve for sodium from 1000 degrees Celsius to 0 degrees Celsius. Sodium has a freezing point of 98 degrees and a boiling point of 883. So all these temperatures, you want to put them on the y-axis. The y-axis will represent the temperature. So here, temperatures in the y-axis, and then the x-axis will have, so because it's a cooling curve, which means you are removing heat. So heat is removed. So that's why I have heat removed as the label for the x-axis. We are removing heat, we are cooling down the substance, and we will start at, so let's put line here. Let's do it on top. Oh, I did a line. I don't know if this thing is easy to use. Okay, that's going to be my 1000 point. 1000, no, 1000. Okay, well, we know it's degrees Celsius because I have it labeled in the temperature, right? So let's say this is 1000 here. To 0. So let's say this here is going to, well, not here, that. Let's say here it's going to be 0. 0. Then we will have 883. So let's put it here. 883. And we have 98 otherwise, so 1/10 of this. I don't know. Let's put it here. Oh, I meant here. Okay. That's my 98 degree Celsius. Okay. So I've put the tick marks for the important temperatures. We are asked to draw that cooling curve from 1000 degrees Celsius to 0 degrees Celsius. We know we will need to stop, do a different way of drawing the line at 883 degrees Celsius for the boiling point or condensation, and then 98 for the freezing point. So it's a cooling curve, which means you want to start at the high temperature and then go down in temperature as you remove heat, right? So that means we will start from the from 1000 here, and we need to go to the, so condensation. It will be called condensation because we are going down here from 1000 degree to 883. It's just cooling down the gas, right? Because if you are above 883, that means you are in the gas phase. So you want to label here that it's the gas. It's just the gas at that point, right? It's very important you understand that. Then when you have reached the 883 degree, you will have the condensation happening. The gas will become a liquid, right? And so when this happens, when condensation occurs, the temperature stays the same until you have completely changed your gas into a liquid. So let's make it large enough here. All the heat that is removed is making the gas become a liquid. And so all that time when the temperature doesn't change, you have a mixture of gas plus liquid. And the temperature cannot change until you have changed all your gas into a liquid. And once this is done, once all the gas is liquid now, then the temperature can decrease again. Sorry. I wanted a line here, going from here. And so the temperature decreases again, and all the way until you reach the freezing point. Because all that time that the temperature decreases again, what you have is only a liquid. right? Because you are in between condensation point and freezing point, right? So that means you have only liquid at that point. And once you have reached the 98 degrees, which is your freezing point, let me make it large enough here. The temperature cannot change. And what happens during that time is that your liquid is changed into a solid. That's your freezing point, right? So the liquid is changed into a solid at the freezing point, right? Freezing point. And the temperature cannot decrease until you have changed all the liquid into a solid. And once you have only a solid, then the temperature can decrease again, and then you go all the way down to 0, right? So, and that portion here is meaning that you have only a solid, and the temperature of the solid is decreasing as you remove heat. So I hope this, oops, this is bent, okay. I hope this makes sense. I know this is not really emphasized in the lecture maybe, but it's good to understand you know, how a cooling curve and a heating curve work.